Markus is currently the CEO of Avant-Garde Materials Simulation Company. His research field is crystal structure prediction. Markus did or is holding a Master of Science in Physics from Heinrich Heine University in Düsseldorf, Germany, and it's holding a PhD in Physics from University of Grenoble, France. He joined the Materials Simulation Ltd in Cambridge, UK, as a product specialist for crystallization and analytical simulations in 1999, and was promoted to product manager in 2001. At Materials Simulation, he became acceleris. Dr. Neumann invented the Excel algorithm for powder indexing. In 2002, Markus founded Avant-Garde Materials Simulation, CIRS, a French company specializing in development of novel methodology for crystal structure prediction, and opened a fully owned subsidiary, Avant-Garde Materials Simulation Deutschland, GmbH, in Freiburg, Germany, in December 2007. He pioneered modern crystal structure prediction and turned into a standard technique used by a large number of pharmaceutical companies all over the world. Markus, the screen is yours.
Thank you very much for this nice introduction. Giving this talk, I feel a tiny little bit like an imposter, because I wouldn't claim that we are developing methods or pioneering methods for quantum crystallography. However, we are really heavy users of quantum crystallography, and so maybe at this meeting and in this lecture series, I represent one of the applied and maybe even industrial branches of quantum crystallography. And so I will talk about the phenomenon which is at the very heart of modern crystal structure prediction, and that is disappearing polymorphs, especially related to the pharmaceuticals industry, and what we can do about it today with our computational tools. So the outline is roughly as this. I will give a short introduction to our company. I will talk about crystal structure prediction theory. I will assess what we know about how many disappearing polymorph cases are potentially out there. I will talk about now not so new anymore energy calculation methods that is able, because of its accuracy, to confirm missing forms beyond doubt. I will show how we use this method to predict phase transitions as a function of temperature. Also, how we predict how we use the same method to predict hydrate, anhydrate phase transitions as a function of relative humidity and temperature. If I have time, I will talk a little bit about high throughput comparison to powder diffraction data. And in the end, I will show how it all comes together to avoid disappearing polymorph cases. A little more about what disappearing polymorph cases actually are. So we already had a nice introduction to the phenomenon of polymorphism. And of course, so the same drug can, in many cases, crystallize in the form of various crystal forms called polymorphs. Those polymorphs may have very different properties, particularly in terms of solubility and dissolution rate. And so the pharma companies, they have to make sure that they always have the same polymorph in their formulation. But now, from time to time, it happens that they start to work with one or several crystal forms, and then after some time, a new form occurs because they have changed some of their processing conditions. And in case it turns out that that form is a thermodynamically stable one, it may actually prevent the crystallization of the forms they had before. And if that happens, then they can't make the same formulations anymore. The new form may have completely different properties. Maybe they lose too much solubility. Maybe they simply cannot formulate it the same way because it's not directly compressible anymore. Anyhow, in that case, those pharma companies, because they can't make the previous forms anymore, they are in deep trouble. And two of the better known cases are ritonavir, so the Abbott case that has already been mentioned, and rotigotine. Rotigotine is a compound that was purchased from another company by UCB. And 1 week after purchase of the compound, they found a new polymorph that was more stable, and that changed everything. So polymorphism and polymorphism accidents can get companies, big pharmaceutical companies, in real financial trouble. And it's estimated for ritonavir that Abbott lost something like $100 million over this case. I say that number again, $100 million over a polymorph accident. And so, of course, for many years, there has been money around to write good software for crystal structure prediction. And that's also how our company was born. Our mission was to try to predict missing forms, more stable missing forms, if they are out there. Now, the main tool that we produce to assess the risk of a late appearing or disappearing polymorph is a crystal energy landscape. So this plot which you see is a list of all low energy crystal structures of a fictive compound plotted in terms of lattice energy and density. The density is not so important, but typically people use the density to have a second dimension to spread out the landscape. And every blue, so this is a fictive landscape, it's just to drive a point across. Every blue circle is a predicted crystal structure, and then in a typical scenario, maybe the red open circles, they are the experimental forms. And if you would have to characterize landscapes by a single number, then that number would be the energy gap between the most stable experimental form and the most stable predicted form. In this case, that energy gap is 0, and that means that the most stable predicted form is the most stable experimental form. And that is typically what the product manager of a pharmaceutical company wants to see to sleep well. But of course, it may look otherwise. So it may look like this. So you get a landscape again, but oh my God, your experimental form is not ranked number 1. It is ranked number 2 or ranked number 3, and there is actually substantial energy difference compared to ranked number 1. And so this means that there would rank number 1 ever crystallize, there would be an energy drop that reduces solubility. And so in this talk, I will try to answer 3 questions. First of all, how often does and can this happen? Secondly, is a predicted more stable form really out there? Or is this just an error of the computation? And finally, if it's really out there, what can we do about it? Before I go to a little bit of theory, this is our current team. So we are, let me count. I think we're 11 or 12, so it fluctuates a little bit from time to time. So I'm in the middle. At the bottom left, you have our second CEO. Then we have 3 people in software development, Hanno, Dmitry, and Martin. We have 3 people in contract research, Kieran, Michelle, and Jakob van der Streek. We have 2 IT staff, Hubert and Stefan. We have recently hired someone for HR tasks, that is Consuelo. We have our secretary, Sandrine. So that's what you see is the entire company is pretty multinational. So we have way too much German, but we also have French, Dutch, Indian, Belarusian, Chino-American, Colombian. So it's a pretty good, pretty fun mix. I have to say some words about crystal structure prediction theory, but honestly, that's probably the toughest part. Because I've been doing this for 20 years now. And right now, we do this with 3 to 4 developers permanently. And every day, every developer tries to do something clever. So there is no simple way anymore to explain how modern crystal structure prediction really works. But I would like to draw your attention to 2 specific things that are general and relatively important for this presentation. The first is that we have to navigate over a wide range of energy methods. And all these energy methods, they have their particular speed accuracy compromise. So at low accuracy and low cost, we have what we call tailor-made force fields. So in our approach, for every compound that we look at, we first fit a force field from scratch to specifically generated ab initio data. And we build a force field that tries to approach ab initio as good as possible, and we call this a tailor-made force field. And for a tailor-made force field, maybe we do 1 crystal minimization on, actually I should switch on my pointer, let me do this. Okay, so can you see my pointer? Good. So for these tailor-made force fields, maybe we do one crystal structure minimization in a second. There is also then at a somewhat higher level of theory, either with WASP or with FHR Ames, we do calculations at the PBE level plus an empirical van der Waals correction, which is our own doing. Then even more expensive, we have better corrections for the PBE0 functional, and we use many body dispersion van der Waals approach developed by Alexander Tkachenko. And then at the very best and highest level, and that's where we calculate the phase transitions, we do PB0 plus NBD plus FVIP. So there we also have an initial calculations of the phonons to get the free energy of the phonons into the plane. Now, if you look at the numbers on the axis, our accuracy improves if we go from dirty to excellent, from 6 kilojoule per mole to 1 kilojoule per mole. The improvement is only a factor of 6. But on the CPU time side, if we go from the force fields to the very best energy calculations, we go from 1 core in 1 second to 1 day on 256 cores. So we pay an improvement in the accuracy of a factor of 6 by something like 10 million-fold increase of the CPU time cost. And of course, if you want to handle this, then you need very special technology to do things as cheaply as possibly as often as you can. And so we have a piece of software. Our piece of software is called GRACE. And what GRACE really implements is a structure generation funnel, but a very sophisticated crystal structure generation funnel, where we will sample billions of structures at the force field level. And then the further we go down the funnel, the more expensive our calculations can become. And at the very, very end, we maybe do 50 structures at the second best level, and then we do a handful of structures at the best level. At some point we did 2 to 5. Today we rather do 10. But so we really, we have this funnel, which is very carefully programmed and which has internal convergence control. So there's nothing manual to do. Each time we go from one step to the next, we try to be 99% sure that we haven't missed a polymorph, and we have rules for how sure we are, so there is full convergence control. And that's really all I will talk about on the theory side, because everything else would be a completely different lecture, and here I'm more focusing on what we can do today. And so, of course, one important question is, how many disappearing polymorph cases are actually potentially out there? I mean, we know it happens. Rotigo, Zodin, Ritonavir, there are others. So it happens, but how many compounds are actually prone to a disappearing polymorph case? And so this is work that, our own work, which gets a little bit outdated, but still it got us some interesting information. So in 2018, for the Faraday discussion meeting in Cambridge on crystal structure prediction, we took the 41 commercial CSP studies that we had at that time, all done in exactly the same way, with exactly the same methods that, well, I mean, some things improved, but it's essentially the same technology that we used in the 3 blind tests before 2018. And so we studied a whole set of 41 commercial meta study and 41 commercial CSPs that we did. The molecule you see, bicalutamide, is actually not in the test set, but it's average complexity for the test set. The number of torsion degrees of freedom peaked around 7, but from 4 to 13. The number of non-hydrogen atoms peaked around 30 to 35, but from 15 to 50. There were 5 hybrids, 2 Twitter ions, 1 salt, but most of the molecules were neutral N hybrids. And the first empirical result of this study was that this energy gap histogram. And please remember, so the second slide or the third slide I showed you was the crystal energy landscape. And I mentioned this gap between the most energy gap, between the most stable experimental and the most stable predicted structure. And this energy gap is shown here for the 41 compounds. And the first bin is the bin where either the experimental form is the most stable one, or it's slightly above the most stable predicted one. And as you can see, actually, for 26 cases, we are in the lowest bin. So most of the time, we have an experimental structure at the bottom, even for pharma compounds and even in 2018. But you also see that some of the bins, higher bins are populated, and they're actually some massively higher bins that are populated. The extreme is 4 kilocalorie per mole, so this is in kilocalorie per mole, 4 kilocalorie per mole. And then rotigotine and ritonavir, they are not in this test set. And for them, we have only plotted the energy difference between form 1, which occurred first, and form 2, which occurred second. Because this somehow delimits a risk region. Yeah? So if crystal structures become as much more stable as in rotigotine or ritonavir, then you are in the dangerous area. Of course, at that time, we wanted to analyze that a little bit further, and we wanted to quantify the risk. And so we actually modeled this. And I do not have more time here to explain the modeling, but we built a very simple stochastic model which only had 3 parameters. The amount of crystals, so the percentage of crystal structures that do not readily crystallize, the accuracy of our calculations, and the factor for the exponential increase of structures in the energy window. And we fitted those results to this histogram. And from that we learned, and that's in the Faraday discussion paper if you want to look it up. I hope I have a reference for the Faraday discussion paper, maybe I don't. So we learned that for 15 to 45% of the thermodynamically, for 15 to 45% of the cases which we got, and we typically get molecules in late development, the thermodynamically stable form was still missing. So roughly for 1/3 of the cases, the thermodynamically more stable form never crystallized. And this histogram is used pretty much by our customers to direct their screening efforts, because it delimits a low-risk region, an intermediate risk region, and a danger zone. And of course, if you are doing 50 compounds per year, then experimentally you will screen less in the low-risk region for compounds that are in the low-risk region, but you will also screen more for compounds that are in the danger zone. Okay. Now, 2018, we still had pretty large computational errors in our energies. And that then suddenly changed by the work of someone else. And so that is this new method, PB0 plus MED plus FWIP. And this method was originally pioneered by Alexander Tkachenko as his PhD student Johannes Heuer. And so for details on the early approach, please look at their work. So this went beyond our work in several respects. So they used the PDE functional, they had better description of van der Waals, and they explicitly calculated the phonos. And this is in part not because of the work they did, it's because they used a code which is called FHI-AIMS, developed by the Fritz Haber Institute in Berlin, which is a very good quantum code with good scaling behavior, cheap PBE0, and that's where Alexander implemented the MBD. And the code is numerically stable enough and has basis sets that allow for free energy calculations on reasonably large supercells. And that brings the phonons into the game. So we really believe that FHI-AIMS is, at least for our purposes, is an excellent DFT code. Now we have our own implementation of this. So actually Grace uses FHI-AIMS a lot, as other ab initio codes. So we don't write our own ab initio codes. We write drivers for ab initio codes, and then everything else is what we do. And we do a couple of things differently. I do not go into the details. For some of the calculations are improved by using our tailor-made force field so that we can go to larger supercells. But there are a couple of other tricks. We are very close to publication, so expect publication before the end of the year. And a lot of the phase transition work you will see will then also be in that in a slightly newer version in that publication. So expected publication before the end of the year. We have the draft. We have a lot of pharma partners, and the problem is to get authorization to publish from all those companies to use their data. That's the main problem. So we re-implemented this method, and then of course something which is really important for us is how accurate are we actually. And because in crystal structure prediction before, no one ever knew how accurate their calculations are, and nobody ever put error bars on their landscapes. So you see landscapes, you see experimental forms on the landscapes, and you do not know at all what this means because you don't have a clue of the error. And so once we had this excellent method in our hands, we try to investigate this. And actually, one set of systems which is pretty good to assess your accuracy in free energy calculations is to look at hydrates. If you have hydrates of two stoichiometries, or an anhydrate and a hydrate, and you have a phase transition between them, and the phase transition is well bracketed in terms of temperature and relative humidity, then that is a measurement of a free energy. And in that measurement, the experimental free energy is zero. The experimental free energy difference is zero. And so then we can computationally calculate the free energy difference and compare to the measurement, which is zero. And that's what has been done in this plot for 16 hydrate and anhydrate phase transitions. So what you see is a probability density for the 16 histogram for the 16 cases. On the x-axis, you have a delta F for the free energy, delta, because it's a difference between experimental data and computational data, and in both cases, it's a free energy difference. So it's delta, it's just that the experimental data is zero by definition. And so when you fit a Gauss distribution to this histogram, you get a sigma of 1.99 kilojoule per mole. Please note that this is a combined computational and experimental error. And for many of the hydrates, since you only had hysteresis curves, the phase transition point is actually not that well defined. So our calculations are more accurate than this. This is an upper limit for our accuracy. And then also, the statistics for 16 cases are not good. This data doesn't contradict the Gauss distribution, but it also doesn't prove the Gauss distribution. Yeah? So this is really Gaussian. It's just the first shot at the distribution. Now, once you know your error, and our entire error theory is a little bit more complicated, and we will get larger errors for large molecules and smaller errors for small molecules, but that will all be in the paper. Once you have your error, you can use this to predict phase transitions with error bars. And the first thing I will look at is, what was this again? Yeah, so before I get to the examples, this is a disclaimer. So all results were generated with our GRACE software, but as I already said, we do not program ab initio codes. So we are heavy users of Turbomul, VASP, and FHI AIMS. Our work would not be possible without the very good software developers that develop those tools. And for some of the examples I show you, I only have examples for relatively small molecules. Please realize that we are doing all these calculations on a daily basis for molecules with 60 atoms or more. But then somebody pays for it because there's a lot of CPU time involved. And if somebody pays for it, then it's confidential. So our best cases I actually cannot show them. So this is a modern crystal energy landscape. It has error bars. It actually, if you look at it really carefully, it has two types of error bars. It has smaller error bars at the bottom. So these are calculations including phonons. And it has larger error bars if you go higher up, because actually the phonon calculations are not affordable for too many structures. So we get more accurate at the bottom and less accurate at the top. And this landscape has error bars. So in the future, if someone shows you a landscape without error bars, ask people about the error bars. Landscapes should have error bars. Then in this particular case, so diffusional has various polymorphs. I show two. One of them is a Z'1 structure, the other one is a Z'2 structure. One is actually disordered, so we had to model the disorder. Disorder can be modeled in free energy calculations. It's still a lot of human labor, but it's not unfeasible. And what I look at next is the relative stability of the two experimental forms as a function of temperature. So here we see the low energy forms as a function of temperature. The colored ones are the experimental polymorphs. The full lines are the actual energies that we calculate. The shaded regions are the actual energies plus the error bar. And you see, of course, that the crossover region, if you take the error bar into account, is still horribly large. Yeah? So experimentalists will laugh at this. Yeah? So the error bar here is something like 150 Kelvin. That is in good agreement with the numbers. So we calculate a phase transition of 580 Kelvin. Experimentally, it's 480. We calculate a heat of transition of 0.667 kilocalorie per mole. The actual heat of transition is 0.478 kilocalorie per mole. So the calculations are not perfect, but before you couldn't say anything about temperature. And today we can, if experimentalists want to crystallize something, we can direct them in the phase diagram. We can tell them, go to lower pressure, go to higher pressure, go to lower temperature, go to higher temperature. And in this particular case, for instance, well, there's another structure out there which becomes very stable at very high temperature, and this is below the melting point. So maybe if you slurry for long enough, and maybe even if you vary the slurrying conditions close to the melting point, or you try different solvents, or God knows what, maybe you find a new polymorph there. So if I had to make a new polymorph of diffusional, that's where I would try. Okay, so we can do this for temperature. We can also do this for relative humidity. So this is the first example. It's predicted versus an experimental solid-state phase diagram for a compound called gandotinib. So the blue line, above the blue line is a confirmed stability region experimentally of the tetrahydrate. Below the orange line is a confirmed stability region of the anhydrate. In between, the experimentalists do not know, and our prediction is not always in between, but it also not too far away from in between, and it captures the temperature dependence quite well. So this is a nice result, but this result is only for 2 experimental polymorphs and doesn't involve a full landscape. Of course, we can play this game for full landscapes. So this is now a full landscape for a small molecule creatine for 2 different temperatures and for different relative humidities. Since we have already talked about temperature, let's only look at the relative humidity. So we only look at the bottom left plot, low relative humidity, and the top left plot, low relative humidity, the bottom left plot, high relative humidity. And so in these landscapes, you see that there's more than one hydration state. Actually, in this early work, there's just the anhydrate and the monohydrate. They have different colors. The anhydrate is magenta, the monohydrate is cyan. If you first look at the low relative humidity plot, so the top one, you see that, first of all, for the anhydrate, virtually all structures at the bottom are experimental structures, and the monohydrate structures are much higher. And then if you go to the bottom plot, which is 100% relative humidity, there the monohydrate is at the bottom of its own landscape, but it's also more stable than the actual anhydrate structures. And always error bars. And so this works pretty well. We have since verified this in many experimental studies. This is about the accuracies that we get. We can trust our error bars, and we can predict relative stability for different stoichiometries on a combined landscape. At the moment, the different stoichiometries really only work for hydrates because there's one adjustable parameter, and we have had only enough data for hydrates. Okay. Now, a challenge we face quite often in our work is that to put the experimental structures on the landscape, we actually have to solve them first. And a study that we do where the experimentalists cannot solve the structure and we cannot solve the structure is wasted money. Either we can put the experimental forms on the landscape, then we have created value, or we can't, and then it all was worth nothing. And as CSP works, moves more and more from late development to early development, the crystal structures are less and less available. So really, you really need very good tools to solve crystal structures from powder diffraction data. And so here I have a couple of slides on very recent development. We call this the, I think I've already said most of these things. Yeah, sorry, I forgot this slide. But so your powder diffraction pattern may look like what you see here. A couple of peaks, a lot of background. And now, of course, whether this form is the blue circle or the red circle changes everything for a pharma customer. It changes from all alarm bells ringing to no more experiments. We stop here and work on something else. And so we have worked on our own matching functionality. This is a module in our software because it's a structure solution factory. That is a tool for high throughput matching of predicted structures to powder diffraction patterns. It builds on work that was originally developed in Martin Ulrich Schmid's group, in particular by Stefan Habermehl. But again, we have our own implementation of this and we have improved it in many different ways. So it would work for phase mixtures. It can construct disordered structures from ordered predicted structures. It can construct structures of high Z prime from structures of low Z prime. It can find preferred orientation. It has a multi-stage procedure that goes from quick cross-correlation to full Rietveld refinement. So we get full Rietveld refinements out of this. And I will show you an example, and that is important. It compiles a full list of alternative solutions. Now, this is an example. It's a simple example. So for bicalutamide, we generated a 25 to 75 phase mixture of form 2 and form 1. It's a pattern that you see, moderate preferred orientation, a little bit of Poisson noise and some background, but not too bad. And then we try to match all 7,340 crystal structures of a prediction against it. And actually, in this case, we assumed, it's just a thought experiment, yeah? We assumed that the customer has already found form number 1. And so a good guess is, yeah, maybe the second polymorph is form number 1. So we're actually looking for a minority component where the majority is form number 1. Can we find this? And so first, to the right, you see an example match against all 7,000 structures with a single component. And there you see the match is not very good. Some peaks are outrightly missed. And then the other one is the automatic, it's all automatic. This is what we get out of our procedure. And it's a match that finds 71% of, it's a mixture of form 1 specified by the user and our rank 28. And it's a 29 to 71 mixture. So that is reasonably close to the mixture, the ratios that we put in. But there is a but, because we have more than one good solution. That is shown in this table. So the green one is the correct solution. The orange ones are pretty close solutions, and the red ones, they are really bad solutions. So there are 5 solutions here which you actually would qualify as something that may be the right solution. Rietveld refinement parameters vary from 4.17 to 5.57. Of course, there's some spread. And actually, the best match is a wrong rank. So this now you may now think this doesn't work, your tool doesn't work, this is rubbish, you can't solve. But that's actually not what it is. And what it is, you see it if you calculate a similarity matrix for the various structures that you get. And so here, it's only a similarity matrix for the relevant structures. And I will not go too much into the details here. Sorry, I lost my presentation. Please give my presentation back. I do not see my presentation anymore. Okay, good. I will try to get back to my presentation. So, and if you look at this curve, you see my presentation again? Do you see my presentation again?
Yes, we see your presentation.
Thank you. So all those other matches, they're very similar to the correct match. And so, of course, we do crystal structure prediction, and crystal structure prediction generates a lot of variations of one crystal structure. And so what our tool gives you is all variations that may potentially match. And then if it gives you one solution, there's only one solution. It gives you 5 solutions, there are 5 solutions. And that means that your experimental data is only telling up to a certain limitation. And so our tool characterizes ambiguity. And that is very important. And then you have to do more energy calculation methods to lift the ambiguity. Now, you have the landscape, you have the experimental form. Is this useful? Can you actually avoid disappearing polymorph cases? And now what I talk about now will actually probably only be really telling for experimentalists, so theorists. But anyway, I think it's understandable. But this is questions that practitioners ask of who stand in a lab. So let's go back to this disappearing polymorph, potential disappearing polymorph landscape. So what can we do for risk mitigation? What are our options? And this is a complete list of options to the extent that I know it. So the first option is to intensify your standard experimental screening, spend more dollars on the experimental techniques. We had cases where customers screened 6 months instead of 1, and that made an entire difference. The next thing is to attempt real rational crystallization experiment design. And in a simple example there is high pressure. If the calculations tell you high pressure will make a target form more stable. Up to 1 gigapascal you can crystallize from solution in diamond anvil cell. Do it. There are a lot of good experimentalists out there who can do it. So rational crystallization experiment design, there are more examples of rational experiments. Then of course you may switch your processing conditions, either to a temperature, pressure, or relative humidity, where you can hope to make a new form. Or defensively, if you cannot make the new form, in production you have to avoid it. So you switch to processing conditions where you will not get it. So you go to a temperature, pressure, or relative humidity range where you are safe. If you have some leeway on your chemical composition because you are formulating a coformer or a salt, then of course something else you can do is you can change your coformer or your counter ion. Because if our results tell us that for 30% of the cases, the most stable form doesn't readily crystallize, it also means that for 70% of the cases, the most stable form readily crystallizes. So change your counter ion, change your coformer, and maybe you're not in trouble anymore. And as a decision of last resort, prepare for a potential disappearing polymorph event. Now, the suggestion you have is mine, which is a stupid physicist suggestion. Use several production sites in different countries with different suppliers. I said this first time I said this as a committee in a pharma company. People immediately told me this is nonsense. We can never do this. It's way too expensive. But then someone made another suggestion. Just have more material on stock. Have 6 months of crystalline material on stock. So should you ever enter into a problem, you have enough. And so that's feasible. So depending on risk analysis, companies may just make different choices in terms of how they operate. Okay, so I think I'm getting close to the end of this, but this is our daily bread and butter. So this is where the money for the current new software development comes from. We do this something like 100, maybe 150 times per year. So a customer comes to us with a molecule. So this is one of the catastrophe cases, rotigotine. Today the customer would come with rotigotine and would tell us, we want to purchase this compound from another company. Is this safe? And we then would generate our landscape. This is early. The structure has not been solved. They would have a powder pattern. We would match against the pattern. We would immediately know where that form is in the landscape. And we would then say, there's something else out there. Has a substantial energy gap. And actually, what we calculate is that it's 8 times less stable. Then they would tell the other company, you are sitting on a ticking time bomb. Either you prove us that this is not dangerous, or we don't buy it. Then one of them would come to us and would ask us, what can we do? We would look at this for a second and would say, you see, the form you're missing is really much denser than the other one. So without even having done a calculation, you have to crystallize under pressure from a diamond anvil cell. And I cannot prove that they would have gotten it, but at least they would have substantially improved their chances of getting it. So that is our daily bread and butter. Okay. Now I have to roll back. I think this is my third last slide. I have to roll back a little bit on my title. My title was predicting disappearing polymorphs by crystal structure prediction. Can we actually do that? And to be completely honest with you, no, because we do not know if a predicted more stable form will ever crystallize. And we do not know if its appearance will hamper the production of the previously known forms. And so we cannot predict a disappearing polymorph event. We can predict the possibility of a disappearing polymorph event. So what we can do is we can check if a more stable crystal packing exists within error bars. We can try to help our customers to try to crystallize a missing form, thus enabling them to potentially witness a disappearing polymorph event where and when it is harmless. For instance, in a secret lab, in a white lab, where everything is destroyed once they have made the new form because maybe they don't want to have the new form. So there are cases where customers really do not want to have a new form. So I tell them don't do any experiments because otherwise you will be in trouble. And of course, we can help people to choose processing conditions or a composition that minimizes the risk of meeting a late appearing more stable form. But this is too complex for a catchy title, and so in the title I've chosen a shortcut. Good, take-home messages. So we have very good statistical evidence that in late development, between 15 and 45% of the thermodynamically stable crystal forms are still missing. They have not been observed. Maybe they will never be observed. Maybe it takes 1,000 years to observe them for the first time. Then nobody cares. If it happens next year, then there are a couple of people in pharma companies that are in big trouble. Crystal structure prediction can be used to identify missing more stable hydrates and anhydrates. Customers tell me late appearing hydrates are much more frequent than late appearing anhydrates. Hydrates are much higher risk for us. Free energy differences as a function of temperature and relative humidity can be computed with an accuracy of about slightly above 1 kilojoule per mole. I should say here for a 60 atom molecule. And these disappearing polymorph cases can be avoided in several ways. Now, before I really stop, I have one last thing to tell you. So, because we have a lot of people in the audience. So we are recruiting. We actually have plenty of open positions. We are searching for 2 computational research scientists and 4 scientific software developers. So in case you find this topic interesting, and there is of course more to it, there is the prediction of crystallizability, there is solubility prediction, there is better tailor-made force fields, there is machine learning. So there's a lot of cool stuff. So if you find this interesting, do not hesitate to apply. Thanks a lot for your attention.
Thank you very much, Markus, for this great lecture, which is now open for questions and comments. And we got the first one, but before we go to those lectures, I would like to ask you one question. Your company is of the size of more or less a research group. You have overcome this barrier of creating your own company. What are the advantages of being, say, leader of the company and being leader of research group at academia? Why have you chosen to start the company?
That's a very good question. So first of all, I worked at the Institut Langevin as a PhD student. It was a cool place, but it was very academic. So very often you wouldn't see what the results would one day good for. So I did my PhD in methyl group tunneling. Yeah? So that is not one of the most exciting areas. And so after that, I really wanted to see something else. I went to a molecular simulation, so later called Acceleris in Cambridge. I had 2 very good years. And I had 1 very bad year. I will not say why it was bad, but companies can turn bad. And so I actually wanted to go back to university. And then my favorite customer gave you a call, and my favorite customer says, I know you want to predict crystal structures. If I would give you your first budget, would you start your company? Ah, okay, good. I said, okay, I do this. Good. And I was young. I thought, give me 3 years, the problem is solved. Yeah. Now, 20 years later, with a lot of people, the problem still is not entirely solved. But when you are 30, yeah, you believe that everything is feasible. And then I got into it. Then there are good years and bad years. There are moments when you have borrowed money, and there are moments when you cannot pay it back. then your company must not stop. So there are moments when you are back against the wall and you actually cannot stop. And that's bad. It's bad for your health, but it's good for your courage because you cannot stop. And then at some point, if it gets good enough, it starts to fly by itself. So now at our current size, what are the advantages and what are the disadvantages? The advantage is as long as you succeed, you tell people that you want to do something, someone is going to give you a contract to just try to do what you want to do. So this is a little bit over. So I mean, we could hire a lot of good people because once we have the good people, we can tell our customers we want to try something new, give us money, they will give us money. What is the downside of it? If you fail once, people do not trust you anymore. So you will just fall off the rope. It's over. Yeah? So you fail by too much. It's over. And also, of course, there are much bigger companies who start chasing you. So as soon as something works, capitalism kicks in, and you have some really big ones after you with really big budgets. And then you have to make a. So we have made a political choice. We stay a family business, and either will work as a family business or it will fail as a family business. At the moment, it works as a family business. And so the advantage is that it's a lot of freedom. Also, it's very applied. You solve theoretical problems, but it's also immediately useful for someone. Yeah, so that's basically it. Yeah, but yeah.
Very interesting, really. Now, shall we go back to scientific questions? We can't hear you. Please unmute yourself.
Yeah. The first question is by Samuel Titit. How does your work compare with the polymorph assessment tool in the CSD materials?
Mm-hmm. Good question. So first of all, what we do is entirely energy-based. So we calculate energies at various levels of theory, including very good free energies. And what the CSD does as a structural database, of course, they try to say something about polymorphism risk comparing to other structures they have in the database. And so I am an energy guy, so I would tend to say that to really avoid disappearing polymorph cases, you really have to calculate the energies because all our low energy structures are good structures, and CSD statistics for all of them would say that these are good structures. So also to the human eye, all those structures are good structures. So I really believe that to really do landscapes and polymorphism risk, you need free energy.
The next question is by Gender Thakur. I'm sorry if I'm pronouncing it wrong. Excellent presentation. Can you please explain how humidity factorizes in factor sales included in landscape? Yes. Humidity factors are included in the landscape.
Yes. So
humidity. Yeah.
Yes. So first of all, we do independent CSPs for the various stoichiometries. So we do the anhydrates, the monohydrates, the dihydrates, hemihydrate, or more or less. And then we bring it all onto a common landscape. To bring it onto the common landscape, we do free energy calculations for all structures. And then there is one trick with an adjustable parameter, but honestly, I'm not going to tell you the trick until it's published. So we want to publish it. We almost have a manuscript. We hope before the end of the year, but I keep the trick to ourselves.
Yeah. Another question by Anna Hosser. Do you take anharmonicity into account? It might be important in the case of phase transition, temperature prediction.
Yeah, yes, absolutely. So we have some corrections for anharmonicity. They are not perfect, yeah. And but that needs to be done. We also have, and this goes beyond the original work of Alexander and Johannes. We also have corrections for imaginary frequencies, for instance. So the main drawback of their method is that when they hit an imaginary frequency, they just say the frequency is not there and they drop the mode. And that's of course not an option because there are crystals which have true imaginary modes. It's not just an artifact of the calculation. There is really a shallow well, and the system evolves between the two sides. And then there's a hell of a lot of free energy in imaginary modes, and you have to do this correctly.
And from Hans Bitbergi, to both speakers actually, it seems that the phenomena discussed here are so complex that we should not try to understand them in terms of limited concept such as quantum crystallography. Instead, we might decide on a long list of observable or computed quantities and use these in the context of machine learning, artificial intelligence.
Yeah, I can reply to that. So this is in principle true. I think that to really learn something, so if I talk about landscapes, to really learn something, you need 1,000 to 10,000 landscapes at least. And so the main problem for machine learning and artificial intelligence is probably that we need to generate those landscapes first. Once we have generated those 10,000 landscapes, you could imagine that the kind of CSP that we are doing gets completely superseded by an artificial intelligence tools. There are reasons why I believe that not, but it could be.
So basically, we still have not enough data yet.
We need many landscapes. So maybe so with our approach, maybe there are something like 200, 300 landscapes out there, but split over several pharma companies who would have to agree that they disclose their very confidential data on their top compounds, so they would never do this. And so so it would have to be done with public money on a public cluster.
Okay, so Parta says agree. Piero, I do not think quantum crystallography is a concept, nor it is limited. Parta, we need more cases though. Yeah.
Yes.
Any more questions?
Okay, we have from Samuel Titi. Can this calculation be performed on a simple computer?
No. So a typical project that we runs on something like 500 cores for 3 months, or 1,500 cores for a month. And so it's also why CSP is such an expensive technique, because you really need all that CPU time to generate the results. And that's also why we are really suffering from the energy cost in Germany at the moment, because CPU time, because of the electricity consumption, has become really expensive. It's not even the amortization of the hardware; it's just the price of electricity.
Yeah. So from this point of view, Markus, are these really expensive calculations? I mean, if you could quantify, for example, the price for such 2-3 months of calculations, in the case somebody is planning this kind of a project.
I know you are curious. You have the right to be so, but I think so you should never talk to your kids about money, and never talk about a scientific presentation about money. Offline, I'm very honest about a lot of things, but not in front of 50 people I cannot see. Yeah? So because who guarantees me that we don't have a competitor in the audience who just wants to understand our pricing model? Yeah? So this is so I understand you have the right to ask the question.
Yeah. Understand we do not have NDA signed, so I understand the situation. Anya?
Another question from Anna Hosel. For what size of supercell calculations take 1 day on? So what kind? How big the supercells you are using? You have 1 day.
The supercells are still relatively modest. So we have found out that we cannot go beyond 8 angstroms per cell lattice vector. So and that's actually the main problem, is whenever we have a lattice direction which is shorter than 8 angstroms, then we have to double in that direction. And so, but the ab initio supercells are relatively large, but of course we have the trick with our tailor-made force fields that we do larger supercells at force field level. So we do a large supercell correction at force field level. But and as I said, so for ab initio the supercells are relatively small. but at least 8 angstroms, and that sometimes makes it fairly big. So imagine you have a plane, so 2 long axes and 1 very short axis, and then you have to double or triple, and then cost just goes through the roof. So the number I show is average over many space groups and many lattices.
And how large molecule? You said
60. I mean, what we do in contract research is typically around 60 atoms. So the pharma companies, they have something called Lipinski's rule of 5, which basically means do not try to develop a drug which has more than so and so many donors except those atoms. And so the 60 is probably good, or 70 is probably good average today in pharma.
Mark Kainowski is asking, what about topological properties in the case of disappearing polymorphs? Do you have any cases of topological studies in terms of Bader's quantum theory of atoms in molecule?
No, we never did this, and I also try to learn new things. So how if you can then tell me how this could help, I'm interested. Very often, so to my understanding, it's really about free energy. So you have an experimental form, and then you have another experimental form. The other experimental form is lower in free energy, and then of course there are the other questions. Why does one form crystallize and the other one doesn't really crystallize? And they are actually we become more descriptor-like because we cannot calculate this exactly. But of course, having done so many landscapes, we have indicators of if something crystallizes or not. But they are also, so I would give the secrets of the trade away. But if next year we have a chance to write something about crystallizability prediction, that would be cool. But yeah, maybe there's something in there.
Stefano Rasiopi. Thanks, Marcus. That was fantastic talk. I would like to know more about the first steps of this funnel procedure, especially how you generate the first pool of structures that is then screened. Maybe I missed that.
So there is a level at which I can talk about it, and a level at which I did not talk about it. So our algorithm belongs to the family of methods which are called Monte Carlo parallel tempering. And that's written in several publications, but that's I would call this unfortunately, and that's, by the way, that's a disadvantage of running a company. Yeah? You do clever things, but you cannot talk about it. And so the very nature of our structure generator, structure generator is certainly a company secret.
Mm-hmm. So, have you done any work on nucleation which might determine the resulting polymorph?
The answer is no, but so this is something that has to be done. Of course, there are several people who do things. I've seen work from Aurora Cabrera-Cruz, for instance, where she really shows that there is that nucleation behavior correlates with the cost of the nucleus. What we try to do at the moment is we try to port our tailor-made force fields so that they would work for nuclei. So we prepare directions in that work, and those that work with our energy methods doesn't have to be carried out by ourselves. So we very much see ourselves as an energy method provider in the future, and that's where we try to go. So we want to provide very good ab initio grade force fields. And we then hope that other people will make an impact on that very important topic.
There is now a very interesting question in electron diffraction: how to crystallize macromolecules small enough for electron diffraction. I mean,
crystals small enough.
Yes, crystals small enough. It sounds like a funny problem at the beginning, but in fact, it's a really very important problem because from the point of view of electron diffraction, these should be like nanocrystals, and this is limiting step at present of the development of electron diffraction studies of macromolecules.
I don't have a solution for that, but in the pharma industry, there is, of course, there is a community of people who prepare formulations for sprays, and they need nanocrystals. So there is a hell of a lot of practical nanocrystallization knowledge out there. And their task is worse than yours. It has to be small, and it always has to be the same size. Mm-hmm. And so that's the only thing I can say. So in the pharma companies, people may actually, for once, have knowledge that may help the academics. But that's the only thing I can say.
Okay, thank you very much. Are there any more questions and comments? As I do not see anybody writing. So Markus, thank you very much for this excellent lecture and discussion.